So I want to go over this concept of the celestial sphere, and this is a well-known concept in astronomy. They place what's called an equatorial grid over the celestial sphere around us, and that is how you can then plot where something is. Now I'm using this flat Earth model as well because this is the working flat Earth model, the best one that I've seen. And at first glance, it looks ridiculous because it's the dome within a dome. You know, it's getting even more silly. But then I found out that in real life, the modern model, there is this exact same dome within a dome. So there's nothing being added to the flat Earth model by having this celestial sphere. It is actually a real thing that exists regardless of the shape of the Earth. Whether the Earth is flat or round, you're going to have this celestial sphere. And I was looking at some astronomy software, and right now we're at the North Pole, and on the flat Earth model, we're also at the North Pole. And you can see where Polaris is. Let's zoom up to Polaris. It's almost at the North Pole. The globe model, they knock it off by a degree. They say it's like 89 degrees instead of exactly 90. Whereas on the flat Earth model, we say it's exactly right at the exact North Pole. Let's see if I can just zoom up on that a little bit. So it is exactly at the North Pole. But you get the point though. And let me just plot the azimuthal grid. So this is essentially this is not a flat Earth grid, but it's the exact point. If you were to have a dome over you, which is like this right here, the celestial dome, it would be 90 degrees. Now, where it gets interesting is when we start changing locations. So let's go to, for example, Belize, where I live. And let's also then set our latitude on the flat Earth model to 17 degrees, which is the GPS location for where I live, Belize City. So, okay, so now here's where the stuff gets interesting. So let's turn off, we can keep the flat Earth one, but the point is, see where Polaris is. Polaris is now at about just under 20, it might be 16, 17. And if you were to look on the flat Earth model's map here, it's also at the 17 degrees, even though in real life it's at the North Pole. So even though physically the object is at the North Pole, it seems that as we get farther away from it, the perspective or the orientation that we view it at reduces. And this makes a lot of sense. So I can adjust this right now. If you look on the right hand side, see how I'm adjusting the latitude? So depending on where I am, Polaris will change. So actually, yeah, that makes sense. If my latitude in Belize is 17 degrees, then that means Polaris will also be about 17 degrees off of the horizon, because that is the North Star. This won't work for other stuff. Everything else will be slightly different. But that then explains how the sunset works and the moon works. So let's see if we can target the moon here in Belize. That'd be beneath us. And then let's go back up here and put the day as the day moves. So you see how the sun comes up. And let me turn off the azimuthal. So this is the equatorial grid right now, what we're seeing. This is what is used in astronomy for mapping and everything. And you can see as the day goes forward, the sun moves along that curve. See that right there? It's really interesting. And this is the real life observations. This is astronomy software, nothing weird that I'm doing. And you can see the moon right behind it too. But they follow the apparent going below and above the horizon, but in real life, they're just on the dome above us moving away. So the exact same thing on this flat Earth model can then be done if I were to adjust the time. So let me turn off the stars, and I think you'll just be able to see the sun and the moon. So if I adjust the time exactly like that, so as the sun comes in above us there, that's like it over there. So it would rise up and then go down, similar to right there, how it will rise up and go down. See how it's rising up? That's the sunrise. And then it's about to set right there. So we can go right back to the sunrise. And let me see if I can zoom up right on that. So that's the sun right there. Similar to here now, if we go back just a little bit, that's the sun rising right there. So what I'm trying to say is that the equatorial grid of the celestial sphere in mainstream astronomy is the exact same thing as the celestial sphere dome within a dome of the flat Earth model. Everything works the same. So you can come to any conclusion you want from that, whether it was reverse engineered. For example, my personal belief is that the flat Earth model is the real observable universe, and that the globe model was reverse engineered. Now that's important because we know that everything works on the globe model, and therefore everything also works on the flat Earth model, because whoever reverse engineered it did a perfect job. And that's why this field is so fascinating to study, because both models work for almost all the observable phenomenon. It's really hard. You can't disprove one model or the other based off of just math alone. Now, in terms of the flat Earth model, this is, I think, a really good new field of study, because not everyone is aware of that. And yeah, you can see too, it's very, very similar. So this guy, I don't know if he actually did an equatorial grid, because I think that's pointing north, or where would okay, no, it is an equatorial grid. Okay, he did do that. You can see then right there how it looks very, very similar to my screen. So that's looking north, and that's me here looking north as well. And let me just see, let me plot. So yeah, so what you'll notice, in terms of an equatorial celestial sphere, the measurements go in hours and degrees. Very, very similar to how GPS works, but they renamed it. So you'll see actually in the top left corner here, let me make this a bigger screen, you got your RA and your declination. I think Right Ascension is what RA stands for. You have your Right Ascension and your declination. And using that, you can then find any object on here. So where was the sun, for example? We can click on the sun, and it's going to tell me right here. The Right Ascension is 2 hours, 49 minutes, 58 seconds, and the declination is positive 16 degrees. And that looks right. So I'm looking on the right hand of my monitor, on the right-hand side. It's in between the 2 and 3 hours. And then up and down, it's supposed to be about 16, and that looks right because it's between the 0 and the 20. The numbers are hard to see because they're kind of hidden on the sides, but it's no different than GPS. They just kind of renamed it so people wouldn't be confused. But the whole thing I'm trying to make is that this celestial sphere in astronomy is the exact same thing that I'm seeing in the flat Earth model. Everything works. And it follows that 1 degree per 69 mile. That's a very observable and proven thing. Yeah, this looks perfect. I actually have to take a screenshot of just this right here because it just shows how everything is so perfect. And that's all I was trying to explain.